Hey folks, Dr. Scott Stevens here with another video on regression. Your project is requiring you to work with multiple regression as well as simple linear regression, but you don't have a video on that yet, so I thought I'd do one to demonstrate some of those things. Um, this problem is problem 9.23 out of the Ragsdale book, and you don't need to read it, but I'll give you a quick idea of what it's about. We're talking about a construction company that is figuring out how much it costs to do the various jobs that it needs to do. There are about 97 of them. This is historical data on 97 jobs. And for each job, we know about 5 different pieces of input information. Whether the wages paid were regular wages or were premium wages. 0 means regular, 1 means premium, which means it's a binary variable. How many units of work were required for the job. How many contracted units of workers were used on the job per day. The level of equipment required, where a higher number indicates more sophisticated equipment. And what city the work actually was done in, city 1 up through city 6. And then, of course, the thing we're trying to predict, total cost in dollars. So what we're going to try to do is to create a model that uses some or all of those 5 inputs to predict the output value. Now, we talked about the principle of parsimony in class, which basically says that actually, as it turns out, the more variables you add into a linear regression, the higher the R-squared value will get. It'll either stay the same or it'll get a bit better. We don't want to include a whole bunch of variables, though, that are giving us virtually nothing. We want to include the variables that have substantial contribution to what's being said, what the equation's saying, but not just throw in everything but the kitchen sink. So how do we figure out what variables to use? Well, one thing we could do is to run the entire model, including all the variables, and take a look at the levels of significance of the variables that are in that model, and then take out the ones that are least significant until we get a model that looks good. That's called backward regression. Okay. We can also do forward regression, which is we find the variable that's most strongly correlated with the output variable, and we throw it in. Then we find the variable that's most strongly correlated with the residuals of that one, and we throw that in, and we keep on going until nothing more is significant. And you can do a combination of this called stepwise, where variables can come in and come out. Software will generally be willing to do this for you, but we're working with only the most rudimentary elements of Excel, so we won't be doing all of that. But I'll point out a couple of things. In trying to get an idea of what variables probably are and aren't important, scatter plots can be a great thing to look at. Let me give you an example. It seems to me that the number of units of work that we have should be pretty strongly correlated with how much a job costs. So I'm going to highlight the number of units of work and the job cost and look at that scatter plot. I'll insert a scatter plot. There we go. And indeed, we do see a positive correlation here. As the number of work units required goes up, the cost in general goes up too. I can add the details to my trend line here, equation and R-squared value. And yeah, my R-squared is about 0.8. That's pretty good. And there's my slope. There's my best straight line. All right, so that looks like a pretty good fit. But how about other variables? For example, the number of contracted units per day. Let's look at that. I'll use the same graph here. I'll simply say that in selecting my data, instead of having my input values being in column B, I'll have my input values being in column C, like this. What's that one look like? Okay. Well, we definitely do have an R-squared, a positive correlation, but the R-squared is quite a bit smaller, as you can see. It's only about 30% as opposed to the 80% we had a moment ago. So this variable does have a positive correlation with the output, but not as much as one might hope. How about if we take a look at the level of equipment that's required? That is column D. So I'll play the same game again. I'll change this C here to D. And look at that graph. And here we go. And here we see the relationship is extremely weak, right? There's almost no positive correlation at all. By the way, this variable also shows quite a bit of heteroscedasticity. That is, the spread of the values at different numbers are quite a bit bigger. Things with equipment level 2 show a wide range of possible costs. Things with equipment level 3 show a very narrow range of costs. So that's kind of violating our assumption that we don't see a pattern in this spread of data as we move from left to right. So, all right, we could look at scatter plots for each of these and get an idea of what they're like. In fact, I have done that. Here's what they end up looking like. Okay, not much going on there with the first variable. A good relationship with the second variable. Decent but not great with the third, as we already saw. The fourth shows virtually nothing, as we saw. The fifth one shows almost nothing as well. Okay, so that's what we're seeing right now. That variable looks promising. That variable looks promising. The others, well, they don't look that great. Although we'll come back and discuss that a little bit later. All right. So back to our entire model. Let's see what it says to do if, in fact, we include all the models, all the variables in our model. If I do that, I would be saying I want all of these things to be inputs and that to be the output. The Excel's histogram tool is perfectly capable of doing that. I'm sorry, regression tool. I've picked regression, and I'm going to say, okay, what output variable do I want? Output is going to be here in column F. These are my output variables, my Y's, and I'm going to say, yes, I do have labels. And my input range, well, I'm going to include all of these variables as being my inputs for right now. All right. And I have a confidence level of 90%. It's a second choice. It'll always give me 95%, but it can give me 90% as well. I'll ask to look at the residual plots like we did in class, and then I'll just go ahead and say, okay, and we'll see what we get. All right. Well, let's look at the model first of all to decide how we feel about it. Looking at this, it looks like the R squared value is pretty good, 83%. The adjusted R squared creates a penalty for having additional variables in the model. We've got a whole pile of variables here. So although the R squared is 0.83, the one we care about more probably is the 0.824. So those extra variables gave us a little extra stuff, but how important really are they in the model? Looking at the model here, you can see here's the entire equation. It would say that the equation is 2040 times the wage variable plus 942 times the units of work variable, and so on, plus the constant term of 43,000. Are these values statistically significant? Well, let's ignore the constant term for the moment, but look at the rest of these guys here. We can see that this variable here and this variable here have extremely large R squared values, as does this one here as well. Those variables don't look like they're statistically significant in the model. On the other hand, the other three variables are showing quite small R squared values, these three here. So our original guess might be that those three variables would be good ones to include in the model, and the other ones not so much. Leave them out. You have to be a little careful with this, because sometimes it turns out that when you remove a variable from a model, that another variable that wasn't significant before now becomes significant. So taking all three of the other ones out at the same time is a little bit dangerous. It's a little bit misleading. But in fact, in this particular case, I can tell you that it wouldn't create any magic if you did it taking them one at a time. If I first, for example, removed this contracted units per day because it's got a p-value of 0.99, then the other ones that are currently not significant would still not be significant. And then when I took out the next one, the last one wouldn't be significant either. So that the three that I've highlighted are actually the only three that I am going to want to keep in my model. There are a few things to say about this though. The first one is this. The variable here of contracted units per day has an extremely high p-value, 0.99, meaning that it's telling you almost nothing. But if you remember with the scatter plots, the contracted units per day actually showed a pretty good correlation, an R value of 0.54 or an R squared of about 0.3. This variable is not important anymore. Why not? Well, because this variable ends up covering a lot of what this variable could tell you. Knowing this variable gives you stronger information about how much the job is going to cost. And the information here is basically contained inside the information here. So that if this variable is here, this one's not very useful. It's not obvious when you look at the program that that would be the case. But it is obvious when you take a look at the output that that variable is way out there. In particular, look, its coefficient, although the best guess for the coefficient is negative 16, it could be anywhere between about negative 3,000 and positive 3,000. Remember that when a variable is insignificant here, when it's bigger than 5%, that this range of p-values is going to, of the confidence interval range is going to include the value 0. And we can see that all the ones here that aren't highlighted do. Zeros in that one, zeros in that one, zeros in that one. It's not in the other ranges, as you can see. For example, this one goes from 800 to 1,000. Zero is certainly not inside that range. These are, of course, the corresponding ranges at 90% confidence rather than 95% confidence. So they're a little skinnier, but you're a little less sure the answer is actually in there. Okay, so let's get rid of those variables that we found to be insignificant and look at the remaining model. I'll do that now by rerunning this thing. Let's go back. We want to keep the intercept, units of work, and the city. All right, so let's go back to the model. Scatter plot, I'm sorry, bit history. I want the intercept, which is not a column. I want units of work and city as my inputs. Well, as you know, Excel's not going to be happy with me with that if I do that because it requires that all the input variables that you use be together in one block of columns. So to do that, I'm going to insert a new column in here and just move that column F so that I put it over here into column C. I'm doing this so that my two input variables that I'm going to use, units of work and city, are sitting right next to each other. Now let's do another regression. I'll go under Data, Data Analysis, and under the Regression tool, I'm going to say my output values are now in column G, these guys. My input values are in columns B and C like this. All right. And I'll do all the other things the same way I had them a moment ago. And again, I'll run this new regression. Okay, here's the new one now. Let's see what we think of it. Well, we've gotten rid of some variables compared to the last time. So the r squared value is actually going to be not quite as good as it was last time. Um, but it's not much worse. As you can see, my r squared is now 0.833, while with the full-blown model, it was 0.8338. In this model, it's 0.8334, a tiny bit less. But what we'd want to compare are the adjusted r squareds. The adjusted r squared for this new model with only two variables is just under 0.83. 0.8299, while the last one with all the variables in was 0.8247. It's not a lot smaller, but it's smaller, which is in favor of our new model, which is these variables. Notice that all these variables are in fact significant. It's kind of interesting that the city variable is significant in this model, because if you go back to the scatter plots and you look at the city variable, you'll see that the r value is about 0.04, which means that the r squared value is about 0.0016, which is a really tiny number, so you wouldn't think it would be significant. Well, it's not if the other variables aren't included in the model, but if you do include the units of work variable, it turns out that those small differences caused by cities can in fact make an important part of the model, and so that value is significant. That said, there are a couple more things to look at. Let's look at the residual plot here. We're always wanting to the residuals that basically show no pattern. You might feel like, well, there certainly is a pattern because they're all clumped over here on the left-hand side and they're spread out on the right-hand side. True, but irrelevant. When we're talking about whether there's a pattern, we're talking about the up and down positioning of those variables. We're talking about whether the residuals show a consistent pattern, for example, getting wider as you move to the left or narrow as you move to the left. Not whether they're clumped this way, but whether they're behaving themselves vertically. Here I see no discernible pattern in the up and down bouncing of those dots, which is what we want when we're doing a regression. Same thing here. I see no discernible pattern in the up and down bouncing of these dots. It's not like creating an arc, for example. We're going bink a dink a dink a dink a dink a dink. We don't have that kind of thing. So the residuals look okay. And that means that this model looks like a decent one for predicting the cost of things. But there are a couple things to point out. First of all, what would the equation actually be? The actual equation would be that number times the number of units of work plus that number times the city variable plus that number to get the entire model. So estimating it, my equation would say that cost, these are rough numbers now, I'm just taking them, is about 941 times units of work, I'll call it UW, plus, oh, sorry, minus, I should say, minus about 4,600, just rounding a little bit, times the city variable, plus 43,000, roughly 43,000 bucks. Okay, so if I gave you a value for the units of work and I gave you a value for the city number, then you could plug into this approximate equation to figure out about how much the job ought to cost on average. It is important to recognize that anytime you do a linear regression, the calculation that you get is saying that if I look at variables, if I look at jobs that have those particular input values, what's the average output value? If you look at the actual pictures, for example, you'll see that, um, well, let's see if I can show it to you nicely. My original scatter plot, the one that we originally did up here, right? Obviously, we're not saying that job 2 always has a cost of this much. There's a great deal of variation. I'm talking about what would the average value for job 2 be? And it's about down here. That's what the equation is telling you. If you stick 2 in this equation and crank it out, you're figuring out what that regression tells you is the average cost for a job of equipment level 2. Okay. So in our model back here, the equation that we would get would give us an average cost. Let's make sure you've got it by doing one example. Suppose the units of work that we had for a job was 30, and suppose that the city it's taking place in is city 5. Okay, then what would the job cost, the average job cost be for a job that has those characteristics? It would be 30 times the units of work variable plus 5 times the city coefficient plus the constant term. So our job estimate would be about $48,000 for, on average, for a job with those input characteristics. And if we change the input characteristics, like make it a city 4 job, we get a different number, and so on. All right. This last point brings up an important point about this data, which is that it makes perfectly good sense to have units of work as an input for this model. It would make sense to say that every additional unit of work would cost you on average the same amount of money. That amount of money here ends up being about 941 bucks. If you have one more unit of work that you need, it goes up by about 941 bucks on average. But the city variable is kind of screwy when you think about that, because I've got 6 different cities, numbered 1 through 6, and the equation is saying that every time the city number goes up by 1, the overall cost goes down by about $4,600. It doesn't make any sense that we talk about every time the city number goes up by 1. After all, city 1 could be Philadelphia and city 2 could be Detroit. Or somebody else might decide that city 1 is Detroit and city 2 is Philadelphia. And that shouldn't make any difference in the model. But here it does, because it's assuming that the city variable is actually counting something, that it's not just an identifier. But it is just an identifier. So what should you actually do about this? I'm not going to be asking you to do this on your project, okay? But what you really should do is to create a whole bunch of binary variables, two-way variables. And the variables would say this: am I talking about city 1 or not? Am I talking about city 2 or not? Am I talking about city 3 or not? City 4 or not? City 5 or not? I only have 5 variables even though I have 6 cities. The reason I would do that is because if all of those variables are 0, if it's not 1, not 2, not 3, not 4, and not 5, then we know it has to be 6, so I don't need a variable for it. If I do the regression that way, I'll show you the result of it, although I wouldn't expect you to be doing that, and certainly not for our project. But let me show you what the result is when we do that. Let me see if I can back up a little bit to what the table used to look like a moment ago. Maybe not. I'm going to pause for a second so I can show you what this result is. Hang on a moment. I thought I paused it. Okay, here's the result. We have a constant term still, as you can see. We still have a variable for units of work, and there's its coefficient. But now, each of these variables is talking about a specific city. So here's what this would mean. Again, this is not going to appear on your project. It's saying this: figure out what the overall cost would be based on the units of work and constant term. If the job is in city 1, add about 19,000 to that. If instead the job is in city 2, add about 24,000 to that. If it's in city 3, subtract about 2,700. If it's in city 4, add about 4,600. If it's in city 5, subtract off 13,000, about 1,300. And if it's in city 6, don't make any changes. So as a result, you get 6 different equations, one for each of the different cities, involving a different constant term because of that bit that was added or subtracted because of what city it was. Okay, that's actually how you handle a categorical variable, which is what the city variable really is. City 2 is not twice as big as city 1. We shouldn't treat it as if it is. However, like I said, you won't be asked to do that. So let's just take one more second and make sure that you're comfortable with the interpretations of what those numbers mean. We'll go back to that last model we were dealing with to make sure that you're comfortable with all of these results. So, all right, what is this saying? It's saying this. We know that the equation of the model is, that's the equation of the best straight line or best plane that we can make based on the dots that we have. But we're not looking for the best fit to just the data in our sample. We're looking for the best fit for the entire population. That's a guess because we don't know the entire population. So what we're saying is our best guess for these coefficients are these numbers here. But we recognize that they might not be perfectly accurate. In fact, when we say that that every unit of work costs an additional 941 on average, we really mean it could be anywhere in that range between $855 and $1,027. And it might not even be in that range. We're 95% confident that it is. Meaning, if we went out and we took another sample from the same population of the same size and we did all the same work that we just did and we got the confidence interval from it, that every time that we do this, 95% of the time, that procedure will work in giving us a confidence interval that does contain the actual value of the coefficient. 5% of the time, it'll screw up. Did it screw up this time? No way to know. But it'll only screw up one time in 20 on average. So we've got a 19 times out of 20 chance that what we just did was fine. This one over here is less sure. It's only right 9 times out of 10, but it's a narrower range. The p-value, if you want to interpret it, is always interpreted this way. If it is in fact true that the coefficient over here is really a zero, then how likely is it that you would see a sample which suggests a non-zero value as strongly as, or even more strongly than, the pattern that we saw? If you go back to our original scatter plot, well, I can't go to that. On this picture here, it's not hard to believe that the actual relationship here is a horizontal line. But on our original picture, with the line being quite steep, it's very difficult to believe that line's really just a horizontal line. So what we're seeing here is that, in fact, yeah, we're extremely confident that number's not just zero. We're extremely confident that number's not just zero in the entire population equation. And we're also pretty darn confident that this one is not. About 1 in 10,000 times, you would see a city coefficient that looks that extreme in your model if the population value were actually equal to zero. So in all three cases, we have pretty strong evidence that, in fact, these things are significant, that there is a linear relationship between the input and the output, that they do belong in the model. That's basically it for this exercise, so I hope it made sense to you. And I see that I'm recording myself, so a little bit of self-reference there. Hope this helps. Good luck on your project. Take care.